Let's talk vectors today. You know that vectors are any quantity that has both a magnitude and a direction. A magnitude is just a number, but also is defined by direction. And when it comes to direction, we could use positive, negative, angles, clockwise, counterclockwise, north, south, east, west. So if you had two vectors, they could either make the total larger or make it smaller. So far, we only have three quantities that do that. Those are displacement, delta x, velocity, and acceleration. But in the future, we're going to have a bunch more. For example, momentums, forces, fields. But energies are not. Two energies can't take away from each other, so energy does not depend on direction. If I were to draw a protractor and measure some line I'm drawing in black there, the magnitude of that line is how long it is, usually in centimeters, or the rebels would do it in inches. But the direction would be the angle it makes, and there are two possible angles you can see here. There's the green and the purple. The green is the measure from the horizontal, which we're going to call x, because x is now horizontal. The purple is the measure from the vertical, y. Now, the green kind of goes up from the x-axis, and the y kind of goes down. So you can label them positive and negative theta as well. Or you could say, instead of positive and negative, you could say clockwise or counterclockwise. And that's what I did there. So when it comes to these kind of ideas, you're going to see how vectors can make complicated things a little bit easier. So in the past, we had situations where like you go forward and then you go backward, and that's it. You know here, if you have go forward and backward, you end up with a little bit forward. For example, if you walk 10 steps forward, 8 steps backward, and the result is 2 steps forward. Not exactly hard vectors. We can represent this as a graph as well. You go 10 forward in some time. I kind of broke it up into two separate sections here. I don't know why. Then you go backwards a little bit. Your overall result is your starting and end points compared. Now I'm labeling in angles here. You can see how they're measured always from the horizontal. And that blue line is your result, we're going to say, at some angle. So the blue line is the overall. It's like in the left-hand picture, the little 2 is the overall. But one looks a lot more complicated. We're going to make it a little bit easier. So let's say we have some vector. The overall magnitude is called the resultant. It's at some angle. So I can draw on the x and y components. Imagine kind of like using the resultant as the hypotenuse of a right triangle. That's the entire point. So I've labeled my x and y components here. And since they're both to the right, and one's right, one's up, I can label them positive. And there's the angle in there. So finding the x and y components of vectors is a key to understanding and manipulating them. And in fact, you could take any walk at some angle and turn it into a right triangle. So let's do an example and see how it's in action. So you walk 20 meters at some angle, 30 degrees from a point. Then you walk directly right or directly east, 7 meters. Your goal is to figure out your overall displacement direction. Hey, how many steps did you end from the start? And at what angular bearing did you end from the start? I'm going to draw in that result in green. That's what I'm trying to find. And the angle I just labeled right there is what I'm trying to find as well. It does not make a nice triangle. In fact, it makes a very ugly triangle. You can see how the two angles are not the same. The 30 degrees is for the 20 meters. It's not for the displacement. In fact, the displacement will be a little bit less angled just by looking at the picture. So instead of doing law of sines, law and cosines, which is actually really hard to work with when you have cases like this, even if you have more than two walks, we're instead going to find the x and y parts of them. Let me draw them in. You can see I'm drawing in the x and y parts. Now for the purple, I'm going to bring that purple line and bring it down because vectors can be moved. It's kind of like copy pasting, moving it down. I'm going to move the blue line right as well. So it's like you're going right, more right, and then a little bit up. And you end up with that green overall displacement angle, which is the exact same in my picture in the top left. And that picture we just drew is a lot simpler. It makes a right triangle. So we're going to find the x and y components of each of the parts and then kind of use them to create this nice right triangle, which you could use sine, cosine, Pythagorean theorem for. So first I'm looking at 20 meters at angle 30. I'm going to draw on the x and y components. They start at the beginning and end at the final result of that 20. So I'm going right and up in this case. X is positive, y is positive as well because I'm going right and up. The x in this case is going to be the adjacent to the angle, which is cosine. So cosine the angle 30 is the adjacent, which is the unknown, over the resultant, which is 20. Solving for that, I'm going to get x is 20 cosine 30, which gives me a result of, I simplified it to 10 root 3, which is I think 17.6 maybe. I wrote it down underneath. And I'm right. So in other words, 20 meters at 30 degrees is like going 17.6 forward and then some amount up. Let's find that amount up. I'm going to do sine for y. Sine of 30 is going to be the opposite, y over the hypotenuse 20. And I get 10. So in other words, going 20 at 30 degrees is like going 17.6 forward and 10 up, meter-wise. Now for the 7, there's no angle, which means the x is positive 7 component and the y is 0. Going 7 east is like going 7 forward and no up and down. So to combine it, we're going to make what's called the x and y table. Now there are two different walks in our result, so we're going to label them as 20 and 7. And then that's my symbol for summation. The x part of the 20 was 17.6, the y part was positive 10. The x part of the 7 is 7, the y part is 0. Add them up, I get 24.3 and 10. So in other words, I'm kind of like redrawing my picture to make you understand. You could see how I can make it simplified and say it's kind of like going 17.6 and 7 more, and then 10 up, which gets me that little picture right there. So that's the picture I'm going to be using. To find the overall result, which is the displacement, I'm going to use the Pythagorean theorem. And doing so gets me 26.29 meters. So I found my displacement. To find the angle, I'm going to use probably tangent. Tangent, opposite of adjacent, 10 over 24.3. To find the angle, I'm going to use inverse tangent. And doing so, I finally get 22.36 degrees from the horizontal. So I just found my result and my angle, which is what I wanted. So to summarize this, before we go into more detail in the next class, the basics from this video I want you to get is that if you have multiple vectors, which for example could be displacements, velocity, accelerations, if you want to combine them to a single value, you need to first find the x and y components of all the ones you have. You need to assign positive and negative values to them and put into an x and y table. Afterward, you then need to find the net x and net y. Then use Pythagorean theorem of those values, as well as tangent, usually inverse tangent, to find the angle, which is your result. And that is something we'll be doing a lot. Furthermore, we also kind of realize that x vectors and y vectors don't actually affect each other. So if we go back to the previous example, if you increase the size of the 7, that would change the final result and angle, but it would not change the y part.